Welcome to our continuing series of lectures on fundamentals of transport processes. Today we will begin the study of dimensions and units. So, the dimension is basically a measure of a quantity. Okay. Measure of a quantity is called dimension. And the unit of that measure, the standard of that measure is what is called a unit. Okay. And so, for example, distance, the measure is the length, and the standard of that measure can be it can be meters, kilometers, feet, etc. Similarly, for time, the measure is time, and the unit can be seconds, minutes, hours, and so on. Okay. And the fundamental principle that we use in dimensional analysis is that there are only 6 fundamental dimensions. That is, all quantities can be expressed in terms of only 6 fundamental dimensions. Okay. You know, there are a large number of quantities that we encounter in everyday life. You know, the area, the volume, the speed, the temperature, the heating, cooling, and so on. But all of these can be expressed in terms of 6 fundamental dimensions, and I will basically list out what they are. One is mass is a fundamental dimension, length, time, okay, temperature, okay, and current is a fundamental dimension, electrical current. So, let me just be more specific here. And the last one is a unit of light. Okay. And the measures of these fundamental units in what is called the SI system of units. Okay, the standardized system of units for each of these. For mass, it is kilogram, length, it is meters, time is seconds, temperature is Kelvin. Okay, we will discuss a little bit about Kelvin and centigrade. Electric current is in amperes, okay, and the light is in what is called as candela. Okay. We shall not be discussing further about this light in our course. Okay. We shall be using all the other units in our course, and for these dimensions we shall have symbols. For mass, we shall term it as m, length as L, time as T. Temperature, so as to not confuse with time, we will denote it by capital theta. Okay. And amperes as A. Okay. So, these are the fundamental dimensions. Okay. And any quantity can be expressed in terms of these fundamental dimensions by basically we have to derive the dimension of any quantity based upon the physical expression in terms of fundamental dimensions. Before I proceed further, let me also say that in some cases the Avogadro number is considered a fundamental dimension. Here we will not consider it as a fundamental dimension simply because it is a number. Okay. It does not have a unit attached to it. The Avogadro number is basically the number of molecules in 1 mole, right. It is like saying that the number of objects in 1 dozen objects is 12. Okay. So, similarly the number of molecules in 1 mole is 6.023 times 10 power 23. Okay. So, this is a number, okay. It does not have a unit attached to it. So, for the present discussion we shall not consider this as a fundamental dimension. All other quantities can be expressed in terms of this fundamental dimension. Okay. For example, velocity. Okay. Okay. Distance moved per unit time. Okay. Speed or velocity is the distance moved per unit time. So, it has dimensions of distance per unit time. Okay. Acceleration is the rate of change of velocity. So, it is velocity divided by time. Okay. It is velocity divided by time or length times t power minus 2. Okay. Angular velocity, okay. So, if I have a rotating object, okay, which is rotating at some velocity, the angular velocity of the solid object, I take the linear velocity, okay, and divide it by the radius. Okay. Okay. So, basically the angular velocity is the linear velocity at a certain distance from the center of rotation divided by the distance from the center of rotation. Okay. So, it has dimensions of velocity divided by distance. Okay. So, this is basically T inverse. Okay. And angular acceleration is the rate of change of angular velocity, that is t power minus 2. Okay. Now, let us come to mechanical quantities. Okay. Force. Okay. Okay. The force is basically the mass times acceleration. Okay. Mass times the acceleration. Okay. So, it is m L t power minus 2, okay. That is the force. Okay. Torque. Okay. The torque exerted on object is, instead of the velocity, we consider the force that is exerted on this object at a certain distance from the center of rotation. Okay. So, the torque is equal to the force tangential to the object multiplied by the distance from the center of rotation. So, if the force is acting at a greater distance, the torque will be greater, okay, even if it is the same force. Okay. So, therefore, the torque has dimensions of force times distance. Okay. Force times the distance, which is m L square t power minus 2. Okay. Work done, okay, force times distance. Okay. It has the same dimension as the torque, m L square t power minus 2. Okay. Energy, okay, has the same dimension as work. The energy has the same dimension as work. Okay. So, it has the same dimension as work, m L square t power minus 2. Okay. Power is the rate at which work is done. Okay. Power is the rate at which work is done, work done per unit time. Okay. So, it has dimensions of work divided by the dimension of time. Okay. M L square t power minus 3. Okay. The other quantity that we had examined in the previous lecture when we defined fields, the density, okay, mass per unit volume, that is mass, and volume has dimensions of length cubed. So, mass per unit has volume has dimensions of m L power minus 3. Okay. Area has dimensions of square of length L square, volume has dimensions of cube of length, that is L cubed. Okay. Concentration concentration is the mass per unit volume of one particular species. So, it has the same dimension as density. Diffusivity. Okay. Okay, so, when we want to calculate the dimension of something, what we need to do is to go to some relationship that involves this quantity in which the dimension of all other quantities are known. Okay. So, the diffusion coefficient or the diffusivity, okay, what does it relate? Okay. Basically, if I have a fluid layer, okay, in which the concentration of a species, okay, let us say is C naught at the bottom surface, C1 at the top surface. Okay. The distance between these two is delta z, okay, and there is a concentration difference between these two which is delta C. Okay. Okay. Then the total mass that is diffusing from one surface to the other, okay, it is directly proportional to the area of these surfaces. Okay, it is directly proportional to the area of these surfaces. Okay, directly proportional to the concentration difference and inversely proportional to the distance between the surfaces. If the separation is larger, the flux will be smaller. Okay. If the concentration difference is larger, then the flux will be larger. Okay. Similarly, if the area is larger, the amount of material transferred is larger. Okay. So, first we should define a flux. Okay. What is the mass flux, okay, going from one surface to the other? The mass flux, as you know, goes from the surface at higher concentration to the surface at lower concentration. Okay. The flux is defined as is equal to mass of solute per unit area into time. That is the amount of solute that is transferred between the two surfaces per unit area per unit time. Okay. So, the dimension of the mass flux okay, is going to be, okay, so I will use this bracket symbol for the dimension of. I will use this bracket symbol denoting the dimension of. Okay. That is equal to the dimension of mass, okay, the dimension of area is length square, the dimension of time. Okay. So, therefore, the mass flux has dimension of m L power minus 2 T inverse, the mass transported per unit area per unit time. Okay. Okay. Now that we have the dimension of mass flux, we can then calculate the dimension of the diffusion coefficient, okay, because we know that mass flux is equal to the dimension of diffusivity, okay, dimension of diffusivity, right, into the difference in concentration divided by the distance. Okay. We know that the dimension of mass flux is m L to the minus 2 T inverse is equal to the dimension of diffusivity into the dimension of concentration. Okay. The dimension of concentration is m L power minus 3, okay, divided by the dimension of distance, which is L. Okay. You do not need these brackets. Yeah, okay. Okay. So, from this relationship I can find out what is the dimension of the diffusion coefficient or the diffusivity. Okay. So, you can easily see that when I multiply this, I have an m times L power minus 4 here and m L to the minus 2 T inverse on the left side, and so if I just cross multiply, I will get the dimension of diffusion coefficient as L square T inverse. Okay. That is the dimension of the mass diffusion coefficient. Okay. So, this is as far as concentration is concerned. Now, let us go on to some thermal properties. Okay. Specific heat. Okay. At constant pressure is Cp. Okay. What is the dimension of specific heat? Okay. So, once again we get that from some known relation in which we know all the quantities except for this specific heat. Okay. We know, for example, that the change in energy of an object, okay, or the change in enthalpy at constant pressure is equal to the mass of the object, the specific heat times the change in the temperature of the object. Okay. So, if I have an object which is being heated or cooled, the change in energy, the thermal energy of that object is equal to the mass times the specific heat times the temperature difference. Okay. So, therefore, the enthalpy or the energy of that object has dimension of mass length square T power minus 2. Okay. On the right side, m has dimensions of mass multiplied by the dimension of specific heat times the change in temperature, which has dimension of temperature. Okay. As I said, I am using this capital theta for temperature. Okay. And therefore, since both sides have to have the same dimension, it implies that the specific heat has dimensions of L square T power minus 2 theta inverse. Okay. You divide throughout by m and theta, okay, on both sides, okay, and you get the dimension as L square T power minus 2 theta inverse. Okay. Good. So, the next will be the heat flux. If I have a fluid layer, okay, of thickness delta Z, okay, across which there is a temperature. Okay, so, there is temperature T naught here and T 1 here. Okay, and the temperature difference is delta T, okay, between the two surfaces, and if the surface has area A, right, there is a transfer of energy from the hotter surface to the colder surface, from the higher temperature to the lower temperature. The transfer of energy is directly proportional to the area A. It is directly proportional to the temperature difference delta T and inversely proportional to the separation delta Z. Okay. Therefore, if I write the flux, okay, heat flux Q, which is the heat transferred per unit area into time. Okay. Okay. The heat flux is defined as the heat transfer per unit area per unit time. Okay. The dimension of Q is the dimension of heat transfer. Okay. Heat transfer is basically an energy. Okay. So, it has dimension m L square T power minus 2. Okay. Area has dimension length square and time has dimension time. Okay. So, therefore, the dimension of heat flux is going to be equal to m T power minus 3. Okay. That is the dimension of the heat flux. Okay. Now, next, what is the dimension of the thermal conductivity? Okay. Okay, that we obtain from a relation which contains the thermal conductivity in it, in which we know all the other quantities. Okay. In this particular case, the thermal conductivity is related to the heat flux and the temperature difference and the separation. Okay. The heat flux is equal to minus the thermal conductivity into delta T divided by delta Z. Okay. The flux from one surface to the other is proportional to the temperature difference, inversely proportional to the distance. Proportionality constant is the thermal conductivity. Okay. Therefore, the dimension of the heat flux, which is m T power minus 3, is equal to the dimension of k, okay, the negative sign has no dimension, into the dimension of temperature divided by the dimension of length. Okay. And if you divide both sides by theta multiplied by length, you get the dimension of the thermal conductivity as m L T power minus 3 theta inverse. Okay. Okay, so this is the dimension of thermal conductivity. Okay. So those are the thermal quantities, and now let us look at some mechanical quantities. Okay. Okay, pressure, which is force per area. Okay. The dimension of pressure will be the dimension of force divided by the dimension of area. Okay. So, m L T power minus 2 divided by L square. Okay. Similarly, the stress, it has the same dimension, force per unit area. Okay. Typically, pressure is acting perpendicular to the surface, whereas the shear stress is acting parallel to the surface, but the stress also has the same dimension as pressure, that is m L inverse T power minus 2. Okay. Viscosity. Okay. We have to get the dimension from some relationship that contains the viscosity and other quantities in which all other quantities are known. Okay. So, that is basically Newton's law for viscosity. Okay. So, if I had a surface, a fluid layer in which there was relative motion between the top and the bottom. So, the top surface was moving with some velocity v, say, and the bottom surface was stationary. Okay, there would be a flow that is generated within this. There was a separation between the two is delta z. Okay. The stress that is exerted due to this fluid flow, okay, the stress exerted due to this fluid flow is going to be equal to the coefficient of viscosity times the difference in the velocity divided by delta z. Okay. Therefore, the dimension of stress has to be the dimension of viscosity times the dimension of velocity divided by the dimension of length. Okay. So, therefore, dimension of stress we just calculated, m L inverse T power minus 2, that is the dimension of stress, is equal to the dimension of viscosity times L T inverse divided by the dimension of length, which is L and not T. Okay. So, you just divide this equation throughout by T inverse, okay, or multiply throughout by T, okay, and you will get the dimension of viscosity as m L inverse T inverse. Okay. Okay. So, that is the dimension of viscosity. Okay. Surface tension, okay, it is a force per unit area acting at a surface. Okay. Surface tension is the force per unit area acting at a surface. Therefore, the dimension of surface tension has to be the dimension of force, which is m L T power minus 2 divided by the dimension of length. Okay. because it is a force per unit length. Okay, so, this has dimension m times t power minus 2. Okay. Elasticity of a solid. Okay. Elasticity of a solid. We will not be dealing too much with elasticity in this course, but I will just tell you what the elasticity of a solid is. Okay. If I had a solid, okay, and I applied a force on it, okay, that solid would deform, okay, and it would undergo what is called strain. Okay, that solid would undergo what is called strain. Okay. If the thickness or the height of the solid is delta z, okay, and this displacement of that solid, okay, at a distance delta z, the displacement at a distance delta z is given by, let us say, delta x, say. Okay. The strain is defined as delta x by delta z. Okay. It is a ratio of two lengths, the length displaced divided by the separation. Okay. So, the strain itself is dimensionless, it is a dimensionless quantity. Strain is change in length divided by length, that is the linear strain. Volumetric strain is change in volume divided by initial volume. Okay. Area strain is change in area divided by initial area, and all of these are dimensionless. Okay. So, strain is dimensionless. Okay. And the dimension of elasticity is determined from the relation that stress is equal to elasticity into the strain. Okay, this is known in various forms. It is usually called the Hooke's law of elasticity, and the coefficient of elasticity is this, okay, is this term over here. Okay, since strain is dimensionless, the elasticity has the same dimension as stress. Okay. It has the same dimension as stress, that is m l t per m l inverse t power minus 2. Okay. Yeah. So, these are some the dimensions of some common mechanical thermal properties. There is one final dimension that I should discuss here, and that is because that comes in when we relate the molecular and the macroscopic description, and that is what is called the Boltzmann constant. Okay. This is a Boltzmann constant. Okay. Okay. The thermal energy, okay, the thermal energy in fluctuations, you know from equipartition, is half kT in each degree of freedom. Okay. So, there is half kT thermal energy in the translational, rotational, vibrational, etc. degrees of freedom. That means that Kb times T, okay, the dimension of that, okay, is the dimension of energy, because Kb times T is an energy. Okay. So, the dimension of Kb times T is the dimension of energy. Okay. That is Kb times the dimension of Kb times theta is equal to m L square t power minus 2. Okay. Therefore, the Boltzmann constant itself has dimension m L square t power minus 2 theta inverse. Okay. So, that is the dimension of the Boltzmann constant. Okay. And the other thing I should note here is that very often, instead of writing Kb times T as the molecular energy, you often write RT as the molar energy. Okay. So, the molar energy is RT of 1 mole of molecules, whereas Kbt is the energy of 1 molecule. Okay. Therefore, the relationship between the ideal gas constant and the Boltzmann constant is that Kb, okay, the energy of 1 molecule divided by temperature, is equal to R, energy of 1 mole divided by Avogadro number. Okay, so, that is the relationship. Avogadro number for 1 mole is 6.023 into 10 power 23, for 1 kilomole is 6.023 into 10 power 26. Okay. When we are dealing with molecular properties, we would prefer to work in terms of the Boltzmann constant rather than the ideal gas constant, because there we know that it is per molecule. Okay. The Boltzmann constant is the energy per molecule. So, in that sense it is more convenient. In the ideal gas law, typically you talk about in terms of the ideal gas constant R, and the proportionality between those two is the Avogadro number. Okay. Here we will discuss in terms of per molecule, and we will use the Boltzmann constant in most situations. I will continue this discussion of dimensional analysis in a little more detail in the next lecture. I will see you then.